Okay, good morning, everyone. How did the homework go? Questions from the homework as usual? Okay, I'm just waiting for you guys to put your homework, so I'll give you a few minutes. Thanks, Grace. You're always their savior. Anybody else? Okay, so we do those and then we proceed. So problem number 55. Okay, what is 55 about? So we have y equal to sine x, y equals 0, on the interval 0 pi, about y equal minus 2. Oh, sorry. Okay, so we have the curve which is bound by y equal to sine x. So we're going to draw it as usual. Okay, 2 sine x. The sine start from the bottom here. It goes up. It goes down. Right here, it's a pi. Then it keeps going, but they only want me on the interval 0 pi. Y equal to 0, that's the x-axis. So this is my curve. That's what the curve we're talking about. And about y equal minus 2. So y equal minus 2 is right here. So this is my axis of rotation. Okay. And we're going to take this picture and rotate it. Okay, rotate it right here. So we're going to have something like that. So it's not really hard to imagine. You have this parabola shape like, and you're going to rotate it. So you get almost like a baseball. If you think about it, it's almost like a baseball when you rotate it. Or an egg or something along those lines. All right, so the way we're going to do it as we do it always. So we're rotating around a line parallel to the x-axis. So we're gonna pick an xi arbitrarily and focus on this one. That's really our focus here. And we're gonna rotate this piece around this line. So when we rotate, this is the center of rotation would be here. So the center of the washer. So first we get a washer because there is a big hole in here. So the center of washer is right there. Oh, sorry, when you rotate this, you don't get a baseball. I forgot that we have a big hole in here. No, you get a baseball with a cylinder taken away from the middle. I'm sorry about that. Okay, so when you rotate this, basically you're gonna get a baseball, but there is a big cylinder cut right through the middle. That's really what the hole is, coming from this opening right there. That's really the picture. So okay, when we rotate this, of course, we're gonna get this washer. And my focus is on the volume of this washer. All right, so the volume of the washer, to be able to find it, we need the inner and the outer radius. Once we determine that, we are done. So we need the inner radius, we need the outer radius, and we need the height of my washer. Okay, so what is the inner radius? The center is right there. The center is here. So as we are rotating this rectangle around the line, my inner is gonna be from here to here. From the axis of rotation till the curve which is closer to the axis of rotation, which is the y equals 0 in this case. And the outer will be from axis of rotation to the farther away curve, which is the top curve in this problem. That's my outer. Now, once once I draw a good picture, I'm actually done with the problem. Absolutely done. Because in this case, my inner is going to be the 2. My outer is from here to here. But as I remember, if this is xi, this point right here is 2 sine of xi. Whatever xi is, this point is on the curve. It means this point is, that's this point. That's the coordinate of this point. So this is 2 sine xi. So I want, that's the inner is from here, the outer radius is from here to here. So it's going to be equal to 2 sine of xi, that's the upper one, plus 2, if you want, plus 2. Or some students like to think about it, the upper value minus the lower value. But minus 2 is equal to 2. So either you just look at the picture, 2 sine xi plus 2, or you say the upper value minus the lower. The upper is 2 sine xi, the lower is minus 2, which give me the same thing. The height in this case, because Wirslet is nothing more than the little delta x. That's the most important part. Once we get it, then we start filling in the detail. So now the idea is that rotate a washer, rotate a rectangle, give me a washer, the volume of a typical washer, is, again, we have to basically memorize this, the radius times, pi times the outer radius square minus the inner radius square. So the outer radius is 2 sine xi plus 2, and the inner radius is 2, the whole thing, delta x. So now we end up with the volume. It's the integral from 0 to pi, because as I always said, that's the interval I have to split into pieces. So it's the integral from 0 to pi of pi times 2 sine x plus 2 square minus 4 dx. And now it's a matter of integrating this piece. Okay, I have to basically distribute. I will have 4 sine square x plus 8 sine x plus 4 minus 4 dx. Now this constant simplify, then I will end up with pi times integral from 0 to pi of 4 sine square x plus 8 sine x dx. Okay. Okay, this is integral. I don't think I taught you how to do it, because you're going to learn how to do it. It works like this. I tried to avoid those problems, but it seems I didn't. Equal pi times. Now, sine x, easy. We know how to find this antiderivative. The question is, what's the antiderivative of sine square? This is something we will spend, I will eventually tell you how to do it, but for now, okay, to find the antiderivative of sine square, we're going to use the following identity. Okay. Sine square x, called the half angle formula. So this is called the half angle formula. And this is a formula from trigonometry. Tells me that the sine square is equal to 1 minus cosine 2x over 2. Okay, so it's nothing more than actually a formula to do that. It's a formula that we learn from trigonometry, and it's called the half angle formula. And tell me that the sine square is equal to 1 minus cosine 2x over x. Now, once we do that, we substitute it in here, the problem becomes back to integral. So this, I go back to my integral. I will have pi times, okay, 4 1 minus cosine 2x over 2 plus 8 sine x. And the whole thing dx. So finally, I will get the 2 and the 4 will give me a 2. And I'm going to basically distribute. I will have 2 minus 2 cosine 2x plus 8 sine x dx. Okay. So the setup, which is matter for us right now. And then once we set up, we have to integrate. And the only problem we have with integration in this particular problem was the sine square, which is, as I said, I've never told you how to do that. So to integrate sine square, because I have no idea what to do with the square, and we use what's called the half angle formula. So I used it. So instead of sine square, I have that. 1 minus cosine 2x over 2. I simplified, I ended up with that. Now the question is to integrate this little piece down here. Okay, 2 is easy. Sine s is easy. Cosine 2x is a little bit problematic because I have an inside function, which is 2x. So I'm gonna, on the side, I'm gonna to isolate cosine 2x. Why I only picked cosine 2x? The derivative of 2 is 2x, I know it. And the derivative of sine is minus cosine, I know it. And the derivative of cosine 2x, I don't know, because I have an inside. So I will isolate it and compute it. Now, since I have an inside function, I need to substitute u equal to x. The du is 2dx. So this would become a half antiderivative of cosine u du. It means a half sine u. It means a half sine 2x. Okay, so I isolated this piece simply because it's not, we don't know what it is. And now the rest will become easy. So finally, I will have pi times antiderivative of 2 is 2x minus 2 times antiderivative of cosine is a half sine 2x plus 8. Antiderivative of sine is minus cosine. The whole thing evaluated between 0 and pi. So a little bit harder because I have the sine square in the picture. And the rest, I guess, it's fairly easy. Those two can simplify and then you proceed. So you guys have to finish, even if I don't finish. All right? Questions about this problem? Okay, so we look at 59 and then we move on. 59, I would like also to, hopefully you guys will give me an answer instead of me doing the talking this time. 59, they have y equal 2 minus x. So that's just a straight line. And y equal 2 minus 2x, another straight line. And it's about x equal to 3. So x equal to 3, which is a line parallel to the y-axis. So let us graph this. Uh, 2 minus x, it means it starts at 2 in here. And it goes down. So it starts at 2 and it goes down, something like that. Okay, and this one also, it starts at 2 and it goes down. If x equal 1, this is a 1, x equal 1, this is 0. And it's gonna go like this. Okay, the slope here is minus 2, so this is actually gonna go deeper. and about the line x equal to 3. And I imagined I definitely wanted, they must have missed something here. Okay. All right, let us see the intersection, this one. This one is right here, 2 minus 2x equal to 0. It means x equal to 1, so this should be a 1. This should be a 2. So these are my region, and x equal to 3 should be a line right here. Am I right?
I think so. That looks about right.
Okay, very good. But they should have told you something, actually. They missed. And also, they should told you also the line x equal to 0. The line y equal to 0. Otherwise, the picture is not really clear. So what?
I think on Math Lab, they said in the first quadrant.
Okay. That makes sense, because they don't say it in the book here. Unless I'm misreading something. No, in the book, they don't say it. That's why it's bothering me. So they must have said something. They have to say either first quadrant, otherwise the graph keep going. And when you rotate this, you get infinite volume, regardless what it is. So they must have said they should have added also y equal to 0. Otherwise, the problem wouldn't make sense at all. And the line x equal to 3, so that's really my axis of rotation. Okay. So to do this problem, because we're rotating around a line parallel to the y-axis, we're going to take horizontal slices. So this is my yi here. And I have to take, remember, this has to be right inside, right there. This is my rectangle. And this is the center of rotation here. So that's the center of those. When I'm going to rotate a rectangle, because there is a big hole in here, when I rotate this, definitely I'm going to get a washer because there is this big hole. So the center of rotation is here, or center of washer. It's important to know where the center of the washer is. Okay. So what is my inner and my outer radius? So I'm going to rotate this piece right there, like this. That's my washer, and that's the big hole. That's the big hole where I'm going the rotation. So my inner radius is from the center of rotation, so it's the horizontal distance from this curve all the way to here. So this is my inner radius. And my outer radius is from this left curve. So I'm going to go like this, left curve all the way to here. Okay, so that's this horizontal distance from the line x equal to 3 to the left curve, that's the outer, and the inner from line x equal to 3 to the right curve, this one. Okay, so now we have to find those inner and radius. All right, how to find them? So what do I need to do? Help me out.
Wouldn't you subtract 3 from each of the other lines that were given?
Mm-hmm. So I need to do, go ahead.
Which one is RN on? Which one? Like,
okay. Yeah, this one,
yeah, that one
is y equal to minus x. Okay, this one here, the left curve, if you want, is 2 minus 2x. So the right curve is the 2 minus x. The left curve is 2 minus 2x. So what do you guys want me to do?
Don't you have to solve for x for each equation?
Exactly. First, I have to solve for x. Y is my variable in this problem. I have to solve for x. Okay, so y is my variable. I'm splitting the region into rectangle, horizontal rectangle. I have to split this interval into pieces to be able to cover this with rectangle. So y is my variable. I have definitely to express x in terms of y. And not because, since I know my yi here, if I want to know the inner circle, I know the distance. I need the horizontal distance from here to this point. But to know this point, I need the xi that correspond to the yi. So first I need to solve for x in terms of y. So we solve y equal to x, y equal 2 minus x will give me x equal 2 minus y. So this is x equal to minus y. I need the other one as well. Y equal 2 minus 2x will give me 2x equal 2 minus y, x equal to minus y over 2. So this would give me x equal to minus y over 2. And now the inner. Who can give me the inner now? Before I pick one. So what's the inner radius? What's the outer radius? And what is the height? All right. If nobody answer, I will pick a student like Andre Williams. I think I've never heard your voice. Andre, can you answer us? Are you with me?
Yes. Would RN be y plus 2?
The inner
Yes.
is equal to what?
Y plus 2.
Y plus 2. Why? Why? This is y. That's why. You see it?
Yeah.
That's why. So why the inner is y plus 2? What is the inner?
The inner linear line would be y equals 2 minus x, correct? And solving
This left or right in this case?
right.
Right will be 2 minus x is 2 minus y.
Yeah. Okay. Yeah. Sorry, I messed up my math.
Okay. So we need from here to here, basically.
Yes.
So what's this point here in terms of y?
That is wouldn't that be y? Where's xi?
No. In terms of
yi.
y. In terms of y. If this is yi,
Mm-hmm.
how much do we have from here to here? What's the coordinate of this point? Let me call this point A. Okay? I'm going to call it A. The y coordinate is yi. If I want this distance here, I need the xi that correspond to it.
Right.
The xi is what? It's the 2 minus the yi. So now I know the yi, I know I need the xi basically. So this point right here is 2 minus the yi.
Okay.
Are you with me?
Yeah.
What's the radius now? Look at the picture.
The radius of Rn?
Yeah. The inner
Is it-
radius.
Oh, it's 2 minus x. I'm okay. Is it not? Hold on. I'm sorry.
That's okay. Don't you're learning. Don't worry about it.
So
Look at the picture. This is from here to here. It's exactly from here to here. Look at the picture. What do you read?
you're flipping across the x-axis.
Don't make it
3.
harder. Don't make it hard. Look, if I tell you what's the distance from here to here, what would you tell me? This is 3.
Oh, from there to 3, would it be 2 minus yi? It'd be plus 3, correct?
Yeah.
Minus negative. No, it's positive 3. So minus 3. Excuse me.
No, so it's me 3 minus 2 minus yi. That's the inner radius. It's the horizontal distance from the axis of rotation to the right curve. So that's the 3 here, minus 2 minus yi, because 2 minus y is from here to here. So basically, you're taking 3, you're taking away that piece from it. That's what you are left with.
Okay. Okay.
Is that clear? A little bit better?
Yeah.
That's the 3. You're taking that away. By taking that away, you are left with that much. Okay, what's the outer radius? Andre, stay with me if you want.
Okay.
So look at it. The outer radius is the horizontal distance from the line y equal to 3 till here, to this point B. That's the outer radius.
3
The
minus, I'm
Go
sorry,
ahead.
3 minus yi, or 3 minus parenthesis yi minus 2.
No.
No.
yi minus 2, no. Because this point B is on the which curve? On the left curve. So
Yeah.
what is the coordinate here?
Excuse 2 minus y over negative 2.
Right, 2 minus yi over 2. Okay, because the point B, yi is given, that's the point B. And what's the height? Means this little bit here.
Delta y.
That's the delta y. My variable is y here. Okay, so volume of a washer. Volume of a washer. Is pi times delta y. The outer radius. I'm not simplifying now because I want to emphasize basically, I'll do the math in a minute. Minus the inner radius square, which is the 3 minus the 2 minus yi. Now, of course, everything should be simplified because we're not going to work with that, but to give me a minute. So now the total volume is the integral. Okay, Andre, stay with me. What are the limits of integration? So you ask yourself, which interval on the y-axis I have to split into pieces to cover my whole region? What's the lower? What's the upper?
You're asking, wait, I'm sorry. Run that by me
Andre,
one more
stay
time.
with me. What are the limit of integration?
The limit of integration is going to be from, wouldn't it be from 1 to 2?
Why from 1 to 2? Which interval, to cover this region, I have to divide the interval from here, because I want to cover it. And
yeah.
rotate each one. I get my
We're-
first washer.
0 to 2, I'm sorry.
0 to 2. That's okay. That's fine. I don't care.
I forgot they were revolving around the y-axis.
Yeah,
y-axis.
a line parallel to the y-axis.
Yeah.
So I'm taking horizontal slices. So I'm taking horizontal slices means I'm dividing the interval along the y-axis into pieces. So that's what you focus on. So integral from 0 to 2 of pi times. So 3 minus 2 minus y over 2, this whole thing squared, minus 3 minus squared that dy. And now I'm going to simplify because obviously we're not going to stay like that. Okay. This is going to give me 3 minus 1. So if you take this term here and you do a little bit of math in your head, this is 1 minus a half y. We're going to give me 3 minus 1. It's a 2 minus a half of y squared minus 3 minus 2. So it's give me a 1 plus y squared dy. That's the setup. Now the rest, I did it several times, this type of problem. You have to distribute here. You have to distribute here. And then whatever you get, then you work with it. Okay, so the last step would be to be able to integrate. I don't know how to, or the simplest way to do it is, okay, distribute, you get a 4 minus 2y plus 1 over 4 y squared minus 1 plus 2y plus y squared dy. Then you combine the y's, You combine the constant term, you combine the y squared, and then you find the antiderivative. At this stage, I leave it up to you. Okay. Questions before we go on? Okay. All right, so today we're going to move on to section, I think it's 6.4, and volume by shell. So section 6.4. Okay. Volumes by shell. You don't have to write a little bit. Let me just introduce the idea, and then we start doing the math. What we developed here is something called volume by washer or by disk. So by disk, it means when your rectangle basically touches the axis of rotation, then rotating it, you get a disk. When your rectangle does not touch the axis of rotation, then you have this big hole. You rotate it, you get a washer. Okay, and that's called the disk and the washers method. But I'm going to set up the following problem in front of you. And I want you to tell me what is the big issue. So this is my curve. As I said, I'm writing so that I don't want you to write. I just want you to listen and tell me what the problem is. So suppose my curve is this one. That's my curve. And this is y equal x cubed, let us say, minus x squared. And I'm going to rotate this around the y-axis. Okay, I'm going to rotate around the y-axis. And let us say this point, I don't know exactly what it is. I forgot to compute it. So I'm going to call it D. I forgot to compute exactly this point. So I have this curve, and I want to rotate it around the y-axis. So it's my axis of rotation. So I'm going to cover this with horizontal slices. Okay, that's what we did. So and I have to rotate each slice, exactly, and I'll get a washer. All right, it is my question here. To be able to do this problem, okay, what do we need to find?
Where it's reflection.
What? What is you using the word reflection? What do you mean by reflection?
Or not reflection. I forgot the word. Hold up.
That's okay.
What's that one? Yeah, basically where the basic rectangle like reflects off of, if you know what I mean. Like
Really. To find the volume of this typical washer, what are the three quantities we need?
Inner and outer radius and height.
Right, we need the inner and the outer radius. So I don't know what you mean. I'm not getting the idea of reflection. Two students used it so far.
sorry about that.
That's okay, that's all right, but I have to see what's in your mind. That's the only way I can help you guys. Okay, so the inner goes from where to where in this problem? From here. So if I call this point A down here, the inner go from the point A is this horizontal distance from here to here. That's the inner. And the outer is from there. So that's the inner. What do you think? So to find the inner, since y is my variable, what do I need to do? Back to you.
Change your equation in terms of y.
Not change it. Change it is not the right word.
Rearrange it, I guess.
What do you mean? Change it.
You're solving.
Solving, right.
I guess solving for y instead of x.
You have to solve for x in terms of y. Is this an easy way to do the problem? Is solving for x in terms of y easy in this scenario? Watch what we have. Y is x cubed minus x squared. And you need to solve for x. Is it an easy problem or a hard problem?
It's easy.
How? If you tell me easy, you solve it for me.
Factor out x squared.
I factor out anything you want.
Okay, never mind.
That's a good try. But what? Is it an easy or a hard problem?
Hard.
If any of you can solve it, it will become easy. I cannot solve it. If I cannot solve it, I doubt any of you can do by now, because it involves cube. You know, even if I give you something like that, x cubed minus x squared minus 5 equals 5. Forget about y for a second. And I tell you solve it. This is a hard problem. I don't think you guys know how to solve it because I don't know how to solve it myself. This is a really, really hard problem. What makes it hard is that you have cube. We've never learned. I mean, there is a formula, but nobody knows this formula. Okay, exactly, because it involves the power of 3. So if I want to solve this problem by this approach that we've learned, the Washer's method, it requires solving for x as in terms of y, which is, as you realize, it's a hard problem. So we have to go around it. We need to do another way to do this problem. So I cannot basically take those slices, those horizontal slices, to solve the problem. I cannot solve this problem by making y my variable and solve for x in terms of y. So that is one way we can do it. We have to keep x my variable, and we have to take those type of rectangle because we want x to be my variable. But then the question is, if my axis of rotation is the y-axis, and I cover my region with those type of rectangle, what's the picture? What's really going to happen? Okay, again, I still don't want you to write because this is actually an easier section than before, but I have to set up the problem for you. So the idea to solve this problem is actually, instead of covering the region, so let us say this is my region, it can be different. Instead of covering it with horizontal, because taking x as a variable is problematic, I'm going to actually cover it with those vertical rectangles. But here's the question. When I take this vertical rectangle and I rotate it around the y-axis, what type of shape I am going to get? So the idea now is we're going to cover it by vertical, and we're going to analyze what do we get, how we're going to fill the volume, because finally we're going to rotate this. We're going to have really a big volume to deal with. What do we get when we rotate this piece? So this is very thin, of course. From here to here, it's a very, very tiny piece. When I rotate it, what am I going to get? I'm going to just draw it for us. So we're going to get something like that.
It's going to be something a lot thicker than just a disc, right?
It's going to be something what?
Something a lot bigger than a disc with a lot more height
exactly. It won't be a disc because in the disc or the washer, the height is your delta x. Remember? That's the delta x. And you have this big hole inside. That's the washer. So the height here is delta x. So now I'm getting basically a cylinder, but the height is big. So it's not really a washer anymore. Okay. So what we are, but this thickness from here to here is very small. So basically, what do you imagine I'm going to get? I'm going to get something basically like a can of pop, if you want. Basically, you're going to get a can of pop where the shell is actually kind of thick. A little bit, not very thick. That's really what we're going to get, something like that. So imagine a mug, I'm drinking my water. So no, I don't think it shows. It's just something like a mug or a can of pop. But what's happening is that there is a thickness to the outer piece. That's exactly what we're going to get. We're going to give this a name and we're going to call it a cylindrical shell. That's what we're going to call cylindrical shell. And now the idea would be, that's the idea. The idea we're going to be, what we're going to do is, whatever my region is, I'm going to split this into rectangle. I mean, we will never change really the basic idea. So we split this into rectangle, and then we're going to rotate each one of them. So the whole volume now is going to be actually filled with those discs. So I will rotate this, and then I'm going to rotate this one. So I'm going to have one disc sitting inside the other. Then I will rotate this big one. So we're going to have another disc. So that's how I'm going to fill my region. So instead of filling it with like a washer on the top of a washer on the top of a washer, I'm going to fill it with those cylinders. And I'm going to keep going. I'm going to get this cylinder and this cylinder. So drawing is actually, as you guys realize, it's really impossible. I mean, not impossible. So this is my region here, and I'm going to fill my whole region with those kind of cylinders. So you can imagine you fill this whole volume with a cylinder, inside a cylinder, inside a cylinder, inside a cylinder, inside a cylinder. And then we're going to add the volume of all those cylinders. So I'm going to show you a very crude video. And I tell you crude, it's not really extremely well done, but to give you a picture in your mind what we are going to do. And then we start doing. So I'm going to share the screen for a little bit. And I'm going to show you, if I manage to do that, a very crude video. All right. This is the picture, something very close to that. Okay. And that's what we're going to do. That's exactly the picture. We're basically going to split it into my rectangle. Okay. And the first focus is on a typical rectangle. That's my typical rectangle. I'm rotating it. You guys see the rotation? That's the shell I am talking about. So I'm going to stop it right here. I want you to see it. That's what we are going to call the cylindrical shell. So this is one rectangle rotated. We're getting this shell. So the height is from the shell is from here all the way to the top. The thickness of the shell, that's what we're going to call the thickness. That's going to be the delta X. It's going to be very, 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 very small. That's the thickness of my cell. And then you have two radius. The radius from the y-axis to the inside, the y-axis to the outside. But those two radius are going to be extremely close to each other because the thickness, which is delta X, is going to be very, very small. Okay, do you all guys see the shell? That's the shell I am talking about. Now, the idea is, okay, let me keep going a little bit. The idea now is to partition. That's exactly the idea. We're going to partition the region and we're going to rotate every rectangle. So they do half rectangle to show you what's really going on inside. So we partition. And those are the cylindrical shell that I want to cut. So that's my first one, inside this one, inside that, inside this, inside this. These are the pieces that they are going to compute their volume. That's really the picture we're going to have. So we're going to add the volume of those little cylinders. Okay. Sometimes I tell my students, you can imagine the cylinder. It's just like if you take an onion and you cut it. Have you ever cut an onion? You will see a ring, inside a ring, inside a ring. That's really, so you have like one piece of onion like a ring. That's just like a cylindrical shell. Another one like a ring, another one like a ring. So you can imagine we are actually filling this volume with exactly like an onion, how it's filled with those shell inside. So this is the picture that we are going to work on. All right. Now the rest, as you will realize in a second, is actually easy. So let's get to work. So that's the picture and that we're going to do. So the first thing we're going to work on is what's the volume of a typical shell? And then we're going to add the shell. So what's a cylindrical shell? Now I start my section 0.4 volume. It's crucial to understand why we are not satisfied with the previous problem. So volume, what do the book call it? Volume by shell. Okay. So first, what is cylindrical shell? So a cylindrical shell. So in this picture below, basically, So the picture below show a cylindrical shell. Cylindrical shell. Okay, so the cylindrical shell is exactly what I'm trying. It's like a can of pop, but there is a certain thickness to the layer, the outer layer of the pop. So this is very small. That's crucial. For us, it's really crucial. That's very, 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 very small. That's important. So that's the thickness of it. So the thickness is very small. We're gonna call this the thickness. Very small. And this is my shell. Okay, you can imagine the thickness right there if you want. Imagine the thickness right there if you want. That's my shell. Okay. The question, what is the volume of a shell? Okay, so that's a cylindrical shell. Now, what is the volume? First, let me call this from here to here. That's the height of the shell. Okay, and that's the thickness. And now I know that we have two radius. So we can have this one, if you want to call it little r, and this one, we can call it big R. All right, so we have the two radius. But if the thickness is very, very small, this radius and this radius are actually very close to each other. So very, very close to each other. Now we're going to find, not find actually, we're going to approximate the volume of a shell. And I use the word approximate. I did not use the word find. We're going to approximate it. So how are we going to approximate? I'm now going to take the shell. Okay, so volume of a shell, write this here. Volume of a shell. And approximate equal to what? All right, how are we going to do that? I'm going to take the shell and open it, you know, flatten it up. Imagine you have a can, you know, and you take it and, okay, the base is, of course, it's hollow. So you have only the outer shell of a can. And you take you just cut it with a scissors and you open it. So you cut it across here. So cut and open. So let's open. Cut horizontally, sorry, vertically and open. What do we get? So cut it along this line from here to here. So you have a scissors, cut it and open it up. What do you think you get?
A rectangle.
Yeah, with a
Or
thick,
a cube.
no, it's a rectangular prism because it's not a cube.
Sure.
Cube is dangerous. It's a
Right.
rectangular prism. Okay, so what we're gonna get is something like a rectangular prism. Sorry. So we get something like that. And there is a thickness, of course, because we have a thickness here, a little bit here.
Why wouldn't it be straight up and down? Like, why is it a prism like that?
What do you mean straight up and down?
Like, how come it's not 90-degree corners?
It is. I
Okay,
just
okay.
draw it because I want to show the thickness. If I draw it like this, it will be
Okay.
hard for me to show thickness.
Okay.
Yeah, you're absolutely right. That's not, yeah. So if this is bothering you, I can straighten it up. Yeah, I mean, I can do it, I don't know.
It's okay. I understand now. I just want to make sure.
Yeah, I thought if I do it this way, you see the thickness better because I'm drawing here. So it doesn't matter. Okay, now I want you to focus with me on the volume of this prism. So, okay, here we are. That's better, I guess. It's the only lecture, the only class where I have to practice drawing before. Never have to do that. Okay, very good. So now what's the volume? So this is when we open it up, we get a prism, rectangular prism. All right, what's the volume of this prism? Help me out.
Length times width times height.
Okay, so let us see. What is the height? The height of a shell is here. Am I right?
Yes.
When I open it, this stays the height. Now, from here to here, in terms of the shell, what is this piece from here to here?
Circumference.
It's the circumference of the circle. Okay, now, whether you use the small radius or whether you use the upper radius, that's where I'm gonna wave my hand a little bit. Because they are very small to each other, I'm gonna take it's almost equal to 2 pi times the radius. And this is really what I am saving. I'm really waving my hand a little bit because r and big R are so small, so I can assume that this is 2 pi r. Okay, the back one is 2 pi times big R, but I'm going to assume they are almost close to each other. So close, I'm going to assume they are the same. Now, what's the thickness from here to here? Now remember, it's not a flat surface, there is a thickness, and that's called the thickness. I'm going to keep calling it the thickness. It's going to be the delta x times delta y. So the volume of a shell is going to be 2 pi r. I'm not going to call it r, I'm going to call it the radius. Whether you take the small or the big, it will never affect the picture because they are very small to each other, times the height of the shell. That's the height of the shell times the thickness. Okay. It is an approximation. As I said, it's not exactly equal because of the problem that I'm assuming R and big R are very, very close to each other. So that's going to be the volume of my typical shell, 2 pi times the radius times the height times the thickness. That's the main formula we will need, and the rest we're going to basically do it easily. Oops. Time is up, I guess. All right. I have to stop. I wasn't aware. My plan was to keep going forever. All right, since time is up, I have to stop. So tomorrow I'll take you from there and you will do a lot of problems that actually deal with shell. So your homework for tomorrow is basically to finish the previous homework. Okay, so I will not assign anything new because I have to, the homework was supposed to be about that, but we ran out of time. All right, so please make sure you finish your homework because when I hit this tomorrow, I want you to be able to actually to know very well the washer, so I can contrast this new method with the washer method and see what are the benefits of each one of them. All right, any questions before we go?
No.
Can you tell me where I can find the problem from the book? Just go to the section, like it's in the book, like 6.3, section 6.3, the problems. It's exactly the same. I don't quite understand the question. Okay. Any other questions? Okay, I'll see you tomorrow, guys. Bye.
Thank you.
Have a good one.
Thank you. Thank you. Bye.